Okay, so when we left off last time, we were talking about carbonyl amine formation. Um, and we were talking about basically taking methyl groups off of amines, and the way that that happens is typically they get oxidized by cytochrome P450. So a lot of drugs have aromatic amines. They are tend to be very bioactive. And if those are aromatic amines in the sense that they're primary and tertiary amines that are directly conjugated, so they're basically substituted anilines. Is this okay?
Yeah.
If they're substituted anilines, they can be easily modified to make reactive electrophilic species, which is interesting. That's basically, you wouldn't think of an aniline as something you'd want to turn into an electrophile, but this is something certainly that happens. And an example of this happening is, for example, how your body processes diazepam. So it's a benzodiazepine, commonly known as Valium, for example, where that methyl group can be removed through that kind of oxidation. And that's the beginning of breaking down Valium, or the kind of the key step into breaking down Valium, so it's no longer an active drug and can be secreted. Another example is this drug where 2-acetyl-aminofluorine, so this is a molecule that becomes carcinogenic after it's hydroxylated. So it's not a carcinogen before, but after your cytochrome P450 works on it, it becomes a carcinogenic electrophile. And the reason some of these carcinogenic electrophiles are formed is that they are these reactive electrophiles, and if they stick around long enough, so that it can be a problem if either an intermediate like this here can end up inactivating an enzyme, right? It can inactivate the cytochrome P450, or it can be attacked by a biological nucleophile. And of course, we always implicate DNA in that as being a problem because that leads to carcinogenesis. Here's another example. We have acetaminophen detected, and notice again how this is another case where we've taken, this is the most electron-rich double bond the way we have it drawn. The other way would be, one of these two double bonds is the most electron. This is what I mean is this is resonance structure, right? In the benzene ring, those double bonds are resonating. But in any case, this is where the electron richness would be on one of these on a pi bond there. So when it is an epoxide is formed, and of course, just to make it clear, this is a symmetric molecule, right? So this would be the most, you could say this is the most electron rich double bond. In any case, once this is oxidized, it's going to form one of these epoxides, right? And these epoxides set things up to be reactive structures. In this case, because we have the alcohol leaving group, you're going to get this quinone-like structure. And again, these will react with glutathione. But some of the other problems with and this is true with acetaminophen, is it can be hepatotoxic, and so that means you don't want to take too much of these kind of drugs like Tylenol. If people that try to basically take too much Tylenol, and by that I mean like an intentional overdose, for an example, get this hepato and kidney toxicity that's quite a problem. And so you get this kind of once you form these electrophiles, they can basically react with other proteins in the liver, and this kind of electrophile is toxic to the liver. And so, and that's also known as alcoholics have more of this kind of radical in their livers from doing various ethanol oxidation products. And so that's one of the reasons they say if you read on a lot of those your ibuprofen or your acetaminophen bottles, it'll say if you have, I forget what it is, like 3 or more alcoholic drinks a day, like, pause and call your doctor before taking this. And that's because alcoholics have a higher risk of this toxicity, but all of these drugs do have this kind of hepatotoxicity that can happen, especially, and that is not likely to happen if you take it at the recommended dose, but it does happen if you take it at a higher dose. There's a couple of other there's some syndromes and stuff that can happen with these non-steroidal anti-inflammatory drugs, but it's a little beyond the scope of what we're talking about right now. Okay, so I was saying before, an overdose on something like Tylenol can cause renal damage, but this isn't due to P450. This is due to another mechanism where you're getting the same kind of products, where you're getting basically these kind of reactive electrophiles that can react with different proteins and this kind of thing. Let's see. For the carbon oxide, so now we're switching gears, right? So we're going to start talking about CO bonds. So before we're talking about CN bonds, now we're going to talk about CO bonds. So this is another example of why you would want to go through methyl ethyl propyl butyl, is that O demethylation and the rate of O dealkylation gets faster, and then it decreases again. So there's kind of propyl is the fastest to dealkylate. So that can you can think about that if you're trying to have some kind of steric effect or lipophilicity in your drug. You've got to weigh that against how that drug's going to act in the body. Maybe propyl would be the best alkyl ether on your drug, but its half-life is so short that it's not, you have to take a pill 6 times a day or something, for example. So that's another one of these trade-offs when you're designing drugs. So cyclopropyl ethers live longer in the plasma, and so they're used a fair bit. So we'll probably see that. If I'm not mistaken, we'll see that in a second. We should actually see it on the next slide, but we're not going to. By that I mean there's a derivative that I should really put up here on the slide that I didn't do. I should put up Naxalone on this slide too. That's all I'm trying to say, but okay. Anyways, so here's an example for codeine and morphine. I love these structures, right? So, I guess not, right? I really like these structures. And so codeine and morphine, O demethylation is really rapid. And another example here is that, so basically codeine and morphine, these are very similar drugs. O demethylation is rapid through this oxidative pathway. Again, for different species, O demethylation only happens here. And so this is, remember that dogs are one of the species that we're studying drugs through. Another example is oxidation of a carbon next to lactone is going to be really common. So here's an example of a anti-inflammatory drug, and it's got this butenolide, and it's going to oxidize here. Um, for carbon sulfur systems, there's a number of ways that you can, there's a number of ways that you can react carbon sulfur systems. You can S-dealkylate it, you can desulfurize it, and you can also S-oxidize. So there's a number of different ways that these can react. So here's an example of thiopental can be turned into pentobarbital. So pentobarbital is a classic sedative. I think it's kind of one of those ones they also mention as like a truth serum or something from back in the 50s. I think a lot of that stuff kind of has been disproven, but in any case, it was one of those ones that's used for that. It's also used as a veterinary sedative in veterinary practice. But anyways, the thiopental, so this X is as the body converts that to CO, which is the same thing that happens in, say, dogs. So this is used a lot in veterinary practice. So the sulfur is really oxidatively ready to do stuff. It's ready to react. So you can easily do these kind of radical oxidations with cytochrome P450. So an example here, right, is what we're happening is that the cytochrome P450 is abstracted an electron from the sulfur. So we have a radical cation and a formal anion here on the cytochrome P450. And then through a rebound mechanism, this oxygen is basically going to transfer to the O minus. This whole O minus is going to transfer. So you could almost draw, you don't really draw an arrow for something like this, but if you were to draw an arrow, it would be from the bonds going there. And that's the O rebound in that case. You can also do H transfer mechanisms, right? So basically what's happening here is that we're breaking one of these radical bonds, we are homolyzing one of the CH2 bonds. That is more coherent. We have a CH2 bond homolysis to transfer a proton back. And that is this H plus transfer. These happen with flavins as well. The flavins are only going to give the sulfoxides. So flavins only do this. Again, the flavins are always the more selective. P450 does both. And you still get this electron transfer mechanism. So here's albendazole, and in this case we're talking about oxidizing this sulfur, and so we both get the S oxidized form and the S dealkylated form. Thiophene are converted into oxides, and this can be a problem because this can bind to liver proteins. So in this case, what they did is this is going to mimic cysteine, so it's 2-mercaptoethanol. And what they showed is that they have cytochrome P450, and now some liver protein, any liver protein that's got a cysteine, is going to act as your biological protein nucleophile and attack in and do nucleophilic attack on this thiophene. Whereas this thiophene's now got this thiophene ring here. This is a thiophene. It now has this ylid structure. It's a sulfoxide, and that means that this is in effect going to be in a reactive double bond. So you're basically doing like a Michael into a conjugated system at that point. So that means it's going to really want to react with something, so cysteine in the liver that can react with an electrophilic double bond. So this is, you got the sulfoxide. You can further um, oxide, oxidize it to a sulfone. There's also oxidative dehalogenation reactions. Those are cool. So this is also these kind of halogenation reactions. So you can imagine those happening, right? Because that chemistry, if we go back to the previous slide, right, this is all going through radical chemistry. So you can imagine that a halogen is going to be okay doing some of this radical chemistry, right? Those halogen bonds we know are pretty happy to do radical chemistry. In this case, right, it's actually not the case, because in this case, what's happening first is that we're actually reacting here to get the carbon radical, and then afterwards we're substituting the hydroxyl group there, and then we eliminate with a 2-electron process to get, at the end of the day, trifluoroacetic acid, actually. Different steroids can be oxidized, so your body is set up to has different aromatases to get rid of or to process steroids, since your body produces steroids and uses them as signaling molecules. So if you take any of these steroidal type structures, your body is set up to oxidize this, and it does this a lot of times with these aromatase enzymes. So a lot of these steroids will have a system here that's alpha beta unsaturated, which can just be oxidized into a molecule that's no longer going to bind to steroid receptors. Another example, this is catechol. So this is this system here, the benzene with 2 OH groups. For some of these morphine and other codeine type structures, if they have a catechol, they can be oxidized to an orthoquinone. Right, so we have an orthoquinone system there. So alcohols, of course, can also be oxidized to aldehydes through the oxidation of alcohol dehydrogenase. Cytochrome P450 does this too, but alcohol dehydrogenase does this. Generally, you want it to go this way. Here's an example where they're able to oxidize this alcohol. So this is abacavir. So this is a reverse transcriptase inhibitor. So it inhibits the ability for the virus, the HIV virus, to replicate its genome. And here the body oxidizes it to the alcohol, to the carboxylic acid. And so this is done by those NAD plus enzymes. So remember, alcohol dehydrogenase and aldehyde dehydrogenase are these NAD plus enzymes. Where they have NAD plus, this is interesting, right? And they're getting NADH back. So they have the forward reaction and the reverse reaction can both happen. And so that's one of the things, is that sometimes there's things that you can actually do. There's things they do in the clinic to push these reactions one way or the other, depending on different poisoning states that a person could encounter. Those arrows are pretty able to be reversed under biological conditions, I would say. Here's an example of oxidation of alcohol to carboxylic acid by cytochrome P450. So this is antihypertensive hypotensive drug. So this is a drug to lower your blood pressure. And so in this case, this is originally, this is an alcohol. When it's the carboxylic acid, it's way more potent. And so we would almost call that a prodrug. It's 10 times this kind of meh difference. You know, if it was like 1,000 times, we'd call it a prodrug, where the drug that you take is not actually the active form of the drug. Okay, so there's a number of reductive reactions that happen during drug metabolism. The nitro, so again, we have ketones going to alcohols and nitros being reduced. Diazo compounds are broken, diazo bonds are broken. N oxides are reduced back to the tertiary amine or tertiary amide. Halogen bonds can be broken through a radical mechanism a lot of times, like we talked, was kind of intuitive. And quinones can be oxidized, so this is reduced through a one electron reduction type mechanism, or in this case, this is actually, these can be 2 electron as well. So this is a old school anticoagulant called warfarin, and so here's notice there's a lot of different reductive reactions or oxidation reactions. Basically, there's a lot of different metabolic processes that can happen, and a lot of this is, we call these aldo. So that's aldehyde reductase and keto reductases. We have sets of these enzymes that are going to get rid of aldehydes and ketones and reduce them using your biological reducing agent back to the alcohol. And once those ketones and aldehydes are reduced, typically that is going to increase the water solubility of the drug as well. And that will make the drug more water soluble. Okay, so here is an example of naltrexone. And so this is an opioid that's used for addiction rehab. And here we have the N, a cyclopropyl amide bond. But notice also, because remember before we said when this was something, so notice how similar this looks to, so this is used in opiate treatment, and if we look at our original opiate, slide is 101. If we look at our original opiate, remember here, this is N-methyl, and we said this N-demethylation is really fast. If it's codeine, the N-demethylation is really fast. Morphine just has the H, so basically codeine is turned into morphine through the alkylation process. And then if it were heroin, right, this would be NH and this would be R. This NCH3 for both codeine and morphine. R is CH3 versus R equals H. But if this is heroin, I know that was a little bit of a synapse not connecting there. Sorry about that. If this were heroin, this would be acetyl groups there, acetyl groups. So you can imagine those are going to have different biodistribution and solubility profiles. But notice this is what the group is here. And now if we look at what we use for treatment, just try to stick that structure in your head when I click back over to it. This is what we're using for treatment. So it's very similar, which I think is really interesting how they interact with these different GPCRs, right? You get different responses. And depends on the species how these are oxidized and what happens. afterwards. That's the point that the slide is supposed to making, but I think there's a number of interesting slides or points that this slide could make. And so here, right, you have you have reduced this ketone to an alcohol, and the stereochemistry varies depending on the species, whether this alcohol is up or down relative to the rest of the molecule. And again, once you reduce it, in this case to the alcohol, that'll up the water solubility. Again, so you can reduce, so we talked before that a lot of the steroids are going to hit aromatases, but they can also be reduced. Alpha beta unsaturated systems can also be reduced to the alcohols, and when they reduce the ketone, they can also reduce the double bond as well. Nitro compounds can be reduced. So this is a 1 electron, and reduction, they can also be done through cytochrome P450 reductases. But these are one electrons type of things at a time. They're skipping through to go to, ultimately they're going from the nitro to the amino. So we can take advantage of that, this nitro reductase, and different species again have different nitro reductase activity. Here's an example using clonazepam. So again, we have this is another benzodiazepine, RNO2 that gets turned into RNH2. And so some of these intermediates, like they can get turned back into the nitro compound. So basically, because the reduction is going through all these unstable intermediates, this is really the stable place that you want to be. You want to be either here or here if you are in something. All of these different nitroso type compounds can be basically oxidized by air, especially if they're aromatic, and so they can be hard to isolate. But that doesn't mean they're not happening in the liver. It just means that it's hard for you, if you're trying to show where your drug goes in the body, it's hard for you to say that with certainty. Sometimes, because you can't isolate some of the intermediates. You have to kind of isolate evidence that the reaction happened. Okay, for azo reduction, again, we said that this bond was going to break when we talked about it before in that table. This bond is going to break, and so this is again another one of these 1 electron processes where this is you're likely going to find either this guy or this guy a lot of times. So here's an example of a drug that's used for ulcerative colitis, and bacteria, actually, your gut microbiota are the ones that are doing this. So bacteria actually have some really cool nitroreductase and other like nitrogen reductase enzymes. And here's an example of them using them. In this case, they have reduced this azo bond. And this is how that drug's getting metabolized. So there's a number of drugs that had these azo groups, and again, these are reverse transcriptase inhibitors. And so some of the, well, I shouldn't say some. So basically, there's a whole class of reverse transcriptase inhibitors that have these azo moieties on them, and in your body, this azido moiety it's reduced into the amine because you can leave with the world's best leaving group, dinitrogen. So you have all these this azido sugar attached to something that looks like a C or a T, And what happens is it looks enough like a RNA building block that the bacteria, or sorry, the viral reverse transcriptase can use it, but it actually messes up the virus's replication, because it basically binds to that reverse transcriptase enzyme, but the enzyme can't continue its processes. So we were saying before, these tertiary amine oxides, those can be reduced quite easily. They're definitely metabolically able to be reduced. They get reduced to the amine. Reductive dehalogenation, again, this is really interesting, right? Like we were talking about this before, that again, we go through that radical, we can go through radicals. This is in the absence of oxygen, right? So this is a different mechanism than what we talked about a little bit before. With halothane, so there's more than one drug breakdown pathway, drug metabolism pathway for a lot of drugs, as you've probably seen by now. And one of the examples of this is here, that halothane can cause hepatitis, and it could quite likely be due. Hepatitis, right, is liver inflammation, and it could be because it's damaging your liver through some of these radical intermediates that are formed. So here's another example of a carboxylation reaction. So this is, again, now we're forming a bond. So the sertraline, so this is a antidepressant molecule, and what happens here is that it's really interesting. So this is the H when you take the drug, and your body converts it first to carboxylic acid, and then eventually is going to add a sugar on this, which makes it, of course, water soluble, but you're gonna detect it at the end of the day as a glucuronide, which is really interesting. Hydrolysis, that we've talked about before, is a big problem. And so this can happen. There's a lot of esterases in the body. So and there's also a number of amidases as well. So amide bonds, ester bonds, these are going to be a problem. Electron withdrawing groups, they make this hydrolysis faster. Conjugation with carbonyls slower. Steric Hendrix slower. So here's an example. Aspirin is going to be hydrolyzed. It's going to hydrolyze this ester back to salicylic acid. And so it's going to be the alcohol and the carboxylic acid. And that's going to happen. All human tissues, your blood, everywhere has got these esterases that are going to do that. So that's what happens to aspirin. So there's hydrolysis by liver enzymes. There's hydrolysis, basically different parts. There's different enzymes catalyze. Only do aliphatic esters. So cocaine has one aliphatic and one aromatic ester. And so those are different enzymes. Amides are more slowly hydrolyzed than esters. Here's an example, right? A procaine. So procaine is they are typically topical analgesics. Procainamide is going to basically be a lot longer acting, and it just has an NH2 instead of an O there, and the amidase activity is slower. So here's another example, is propanidid, where you don't get in this case, you don't get the amide hydrolysis. You have a really sterically, or a fairly sterically hindered amide there too, which helps slow it down a little bit. There's some that do go fast, and so here's so basically, as a rule, you should probably be worried if you have an amide in your drug that it could get hydrolyzed, and you need to be testing that or following that when you do your metabolism studies, or have kind of an asterisk on that amide or that compound with that amide when you're doing your studies, because it's likely that you're going to run into some of this different hydrolysis issues. Another issue is, again, there's different enantiomer toxicities. This is just to remind you again that your body's chiral and recognizes chiral proteins are chiral, and they recognize chiral substrates. And an example, this can be seen in different enantiomers of drugs having different actions. This is really cool too, is right, you have the R ester is hydrolyzed in the liver, but the S ester is hydrolyzed in the brain. So this is an example. So they're talking about this having this stereocenter coming either out of the plane or back behind the plane. This is oxazepam, which is another one of those benzodiazepines. The enantiomers can be differentially metabolized. So here's an example of a drug where the S enantiomer is going to be metabolized by the liver, and the R enantiomer is going to be metabolized by an esterase. Okay, so phase 2 transformation. So we talked about this a bit. They produce, they deactivate the drug by producing water-soluble metabolites that are readily excreted. And if they don't, those groups aren't there, phase 1 will introduce it. And some drugs are excreted without any metabolism at all. So here's an example, which is pregabalin. That's excreted without any metabolism at all. But here's some phase 2 transformations that we talked about before, which is, the one that we actually have talked about before, I think, really is adding the glutathione, and we briefly touched on acetylation and glucuronide. So where you form, so in this case, you see that you add the sugar to it, like we were talking about a second ago with sertraline. You can add a sulfate. So this is another phase 2 transformation. You can add glycine and glutamine to it. There's glycine in acyltransferases, glutamine in acyltransferases, sulfotransferases. The transferase enzyme is a UDP, a glucuronosyl transferase. And so this is, you have the uridine here is the leaving group, and this is the sugar that you're going to attach there at the anomeric carbon, and that's what's going to be attached to your drug that's getting metabolized. So again, glutathione, arene with the X, and arene oxide and epoxide, carbocation are related. Methyl groups sometimes can be added on. So here's an example where you want to use that, a methyl transferase, so an S-adenosine methyl transferase. So this is an example of that with the methyl groups being transferred. Okay, so You make, this is the whole, for glucuronidation, this is the substrate for the enzyme. This is the energetic currency that gets transferred. This whole, there's a diphosphate here, and this group's called a uridine. And so this is what is, just like an ADP, just like ADP as a leaving group, this is like adenosine diphosphate. This UDP is what the leaving group is, what's driving this reaction forward. And so RXH is going to be NH or OH of your drug. And this is what's driving that reaction forward. And so then you lose UDP, which is going to have a similar energetic like driving force like ADP. So there's a number, so these, you want to be looking for those because there's a number of different compounds that do this. We've talked about a lot of these actually before. Certainly acetaminophen, there's chloramphenicol, it's an antibiotic. So there's a number of ones that do this. There's a number of diseases that are associated with not being able to do this. You generally, if you have this, a problem with this, you will notice it really early on in life. Because this is going to affect both the drug accumulation, and it can also, it's going to affect your body's ability to live, basically. And so these kind of inborn diseases are generally detected early. So here's another example. This is really interesting, right? Rats, guinea pigs, and rabbits were all very similar, but we're the only ones that are going to glucuronidate this drug at this sulfonamide group here. So you can also form different glucuronides. So sugars are really complicated, and their enzymes are really complicated too. They're really complex biopolymers. You can also are going to need to watch out for things like stereospecific, where you're getting the two isomers, but liver and kidney is only going to give you one isomer, and the intestinal enzyme's going to only react with the other isomer. So that's something else you have to look for. Sulfate conjugation. Sulfate conjugation happens as well. It's less common, but here we can actually use ATP to do this. And so what you do is you add the sulfate onto a phenol. So you can do both of them. Here's an example of albuterol oxidation, where both of these things can happen, but you actually sulfate it faster. So that's one of the ways that albuterol gets processed in the body, which is in inhalers, a drug in inhalers for asthma. Phenacetin, so this is one of those non-steroidal anti-inflammatory drugs, and those actually can become toxic through this process, through that sulfotransferase process. You've created an electrophile. So next is amino acid conjugation. So there's a number of different, well, basically, let's say there's a couple, I wouldn't say a number, there's a couple of different enzymes. Mostly it's glycine, but in primates it's glutamine. So here's an example of this, where first, look at all the amazing, right? We've got a lot of different a lot of enzymatic work that's happening to get the drug to the form that's ultimately excreted. So it can be excreted here, or it can be you're demethylating, demethylating, getting rid of turning it into an aldehyde. That you're going to bring in another enzyme, turn it into carboxylic acid, and then you're going to couple the carboxylic acid to glycine. You brought in glycine here, and then it's excreted. Glutathione conjugation. So notice how much of their 5 to 10 millimolar in liver and kidneys. It's smart that we have that much there because it's a scavenger of electrophiles, and we've seen that we make a lot of electrophiles during metabolism, drug metabolism. We're creating all these electrophiles, which could be bad news if they hit DNA. So it's a good thing that we have a lot of this in our liver and kidneys, so that when we have all our toxins that we love, we can safely get rid of them. So here's an example. This is nitroglycerin. Again, this is used for chest pain. It is the same nitroglycerin of the explosives. And here we can see how this is going to be reacting with glutathione. What's another? Oh, morphine. That's a good one too. It's a fave. We have, again, the morphine. If it's oxidized, right, we have the alpha-beta unsaturated system. We can form a reactive, we can do a conjugate addition reaction with glutathione to form something that's more soluble. This can also be further conjugated. The glutathione conjugation can be further through glutamyl transpeptidases, cysteinoglycine dipeptidases, and other cysteine conjugation enzymes. This can be further metabolized. So there's also water conjugation. So we talked about this earlier when we were talking about how you could oxidize a double bond to an epoxide, and then you had epoxide hydrolases, hydrolase reactions that were going to turn that epoxide into a diol. So if you remember that, they were turning the epoxide into a diol. Here's another example of that happening. Or here's another reference to that, because that process, we didn't mention it then, but that process was actually be considered phase 2 metabolism because you've added in another water that was generated or that was conjugated from the enzyme. So its source was another enzymatic reaction. Acetylation. This is important for xenobiotics, so that's also our drugs. And it converts an amine to an amide. It's different in different populations. And so this is another example, right? You can see that there's a lot of diversity in how drugs are metabolized in the body. So they all may have the same mechanism of action. They all can hit the same receptor, but what your body does afterwards with drugs, there's a lot of differences. There's a lot of differences in species. There's a lot of differences in populations, etc. And so this can be something that you have to watch out for, because people with different genetic makeups, or people just in general, can have different responses due to whatever proteins they happen to be expressing. Okay, fatty acid and cholesterol conjugation. So if you have a hydroxyl, the carboxylic acid groups, they can basically be conjugated to fatty acids. So an example of this is you add in, we have this methyltransferase. So this is kind of the winner of the methyltransferase, which is S-adenosine Methionine, acetylmethionine. So this is going to be your biological methylation reagent of choice. And this can methylate a lot of different compounds. In drug metabolism, it's kind of minor, but and that makes sense, right? Because it reduces polarity and hydrophilicity, so that kind of sucks. But in normal metabolism, in your regular homeostasis metabolism that keeps you alive, it's very important, S-adenosine, this methylation capacity that you have. So one of the other things to note here is that if you have, your body has these catechol methyltransferases, but if you have a 1,3 compound, this isn't a catechol anymore. It has to be a vicinal diol. So it has to be 1,2. You can't have it be 1,3. And so that can be something you can play with. And we've seen that before in some of our analogs of catechols, etc. We've played with this before in our homework problems. You can also, again, you can methylate hydroxyls. It is possible, but it doesn't happen again a lot because it's kind of going again the wrong direction. You can get O-methylation, and you can get N-methylation as well. S-methylation also can happen. So here's a couple. We had captopril. We talked about that story before when we were talking about blood pressure. The story of blood pressure ACE inhibitors. Actually, no, not ACE. Angiotensin 2. Okay. So we've talked about toxophore before, and we need to think about it again in the context of drug metabolism. So what can happen is that the drug isn't a toxophore itself, but once it's metabolized, it can become a toxic species. So this can be hepatic, renal, etc. toxicity. And so one of the other things that can happen is that these electrophilic compounds can cause adverse drug reactions that can be immune responses as well. So if it's able to form this covalent conjugate, we don't know a ton about how this happens, but some people can form immune responses, and this is because we still don't understand a lot about how you form allergies to a chemical compound. We're still learning that. So an example of this is atorvastatin. So this, and the thing is, atorvastatin, or not an example of this. Sorry, this is it's an example of this, but that's not the story that I want to tell you with this slide. The story that I want to tell you with this slide is that it forms this reactive intermediate, which could give you either cancer or another toxicity or this immune response. But you only have to take 10 milligrams of it a day. So it's fine. And so liver microsomes are one of these. It's basically a toxicity testing setup that we can do in vitro as a way to test liver toxicity or metabolism. However, this drug, lemiracoxib, is not approved because you have to take 40 times as much. And so you form the same species basically, right? This is even more, this is probably going to be even more reactive. But you form the same species, but you take 40 times more, and that's too much. You're gonna start seeing those, a lot more of that, the carcinogen, either the carcinogenic, the toxic, or the immune response. So honestly, you'll probably see some of this here, but it might be so small that it's hard to, so infrequent occurrence that it is not enough to take the drug off the market. So sometimes it's not metabolized fast enough. So an example of this was celecoxib. So celecoxib. Sorry, I always just think of it as Celebrex in my head. So, anyways, in this case, this is an arthritis drug. Here's your initial half-life, and here's your shortened half-life. And so notice this. They shortened it because the parachloro was changed to a paramethyl because the carbon next to an aromatic group undergoes cytochrome P450 oxidation. So what does that mean? This wasn't getting oxidized by cytochrome P450. So the dogs, you could give it to a dog and it would stay in its plasma for a month. Because cytochrome P450 couldn't do crap with it. None of the other enzymes couldn't do crap with it. So what they did was they added this methyl group next to an aromatic enzyme. And now cytochrome P450 knows exactly what to do with that. It's gonna oxygenate. It's gonna put a OH there. It knows exactly how to handle that. And so once it does that, then it can start the metabolism process. So that compound, so this is what's called a hard drug. This is really specialized. Obviously, you've heard other hard drugs. I'm sure if you've ever watched a police show in your life or went to DARE or something, like, you know that there's different terms for hard and soft drugs. What they mean here is hard and soft in terms of this is hard in terms of its metabolism. This is soft in terms of its ability to be metabolized. So you want to have a soft drug that is predictably and controllably metabolized, and that's going to give you non-toxic and inactive products. That's what you want. And so here's the characteristics. So this is kind of nice. Here's these rules. Is that sometimes you have to do this. Is that if you're having some metabolism issue with your initial lead compound, you want to find something that's going to be as close in structure to the lead as possible, but is going to have this metabolically sensitive moiety so that you can figure out how the drug's going to be metabolized. And so when you would use these rules, a lot of times is that your drug is a hard drug, so it's not getting metabolized, or there's the metabolism's really confusing, or that your drug's got some kind of toxic or reactive intermediate that's being formed, and so you want to add in a group so you know exactly what the metabolism is going to be like, so you know exactly when doctors should be giving a dose of the drug, and you also know that there's not going to be a lot of drug-drug interactions or this kind of thing. You want to have that built in when you design your drugs. Another thing that you can do, so this is kind of pretty interesting, is that you knew what the biologically inactive compound, and you basically design your drug so that it's metabolized to this biologically inactive compound. So that's pretty cool. That can't happen a lot of the time, but when it can happen, it's a really smart way to design a drug. All right, that's all from me.